So we are still talking about polar curves. So we have now curves which are given as follows. R is equal to f of theta, but r and theta do not have the meaning of Cartesian coordinates, but they are polar coordinates. And we saw last time already that, we saw last time already some examples for polar curves. For instance, if you have this curve here, this polar curve, then this is the so-called cardioid. So just to look once more at the graph, so if you plot the polar curve in the usual Cartesian coordinate system, then for this curve you get, so you see that if theta is equal to 0, you start at 1, and then as theta is growing, you move up. When theta is between 0 and pi half, the r is increasing from 1 to 2, so you get something like this here. And as theta is increasing from pi half to pi, the r is going back to 1. And then as theta is increasing from pi to 3 pi half, the r is going to 0. Is decreasing from 1 to 0, so you get something like this here, something like this here. Okay, so these are so-called polar curves where you interpret r and theta as polar coordinates of a point. But of course, we are going to plot the curve in the usual Cartesian coordinate system. Now, what we want to do today is, okay, we want to discuss properties of such polar curves. For instance, we want to know, okay, for instance, for this curve here, where are the horizontal and vertical tangents and so on, questions like this. Or we want to know, okay, how, what is the arc length of the curve you see here? Or what is the area enclosed by the curve? Now, first for tangents. This is not very complicated because, as I said already last time, a polar curve is just a special case of a parametric curve. Namely, the x is equal to, because there are formulas how to convert polar coordinates into Cartesian coordinates. So x is equal to r times the cosine of theta, y is equal to r times the sine of theta. So if you have a point given in polar coordinates r and theta, then that's the two formulas you're going to use in order to convert the point in polar representation into a point in Cartesian representation. And since the polar curve is given here by this equation, we see that the first equation becomes f of theta times the cosine of theta, and the second equation becomes f of theta times the sine of theta. Okay, and by looking at the problem like this, we see that a polar curve is just a special case of a parametric curve, and these are here the parametric equations. But for a parametric curve, we know how to compute, for instance, tangents. So the tangent is equal to the derivative of y with respect to the parameter over the derivative of x with respect to the parameter. So that's the usual formula for computing derivatives of curves given by parametric equations. Okay, so here you have here you have to use the product rule. So you have the derivative of f with respect to theta times the sine of theta plus f of theta times the cosine of theta over, and here you have the derivative of f with respect to theta times the cosine of theta minus f of theta times the sine of theta. Okay, so for instance, if we look at the cardioid, okay, where we have r is equal to 1 plus the sine of theta, okay, then you just have to use this formula. So dy over dx is equal to, so the derivative of this function with respect to theta is the cosine of theta, so you have the cosine of theta times the sine of theta plus 1 plus the sine of theta times the cosine of theta over, here you have the cosine square of theta minus, and then you have 1 plus sine of theta times sine of theta. Okay, so for instance, you can simplify this a little bit. So in the denominator, you have the cosine of, you can take out the cosine of theta. So what is left is 1 plus 2 times the sine of theta. And in the denominator, you can replace this here by 1 minus sine square of theta. Then we have here, we have from here another minus sine square of theta. So we have minus 2 sine square of theta, and then minus sine of theta. Okay, so this becomes the cosine of theta, 1 plus twice the sine of theta. And this here is 1 minus 2 times the sine of theta times 1 plus the sine of theta. Okay, so for instance, if you're interested in, of course, we are not going to memorize this formula here. We just recall how to derive the formula, and the only thing we have to memorize is the formula for the tangent of a polar curve to a polar curve. So, for instance, if we want to know here now where are the horizontal and vertical tangents, then for the horizontal tangents we have to equate the denominator to 0. The numerator to 0, so you get this here for the horizontal tangents. So you see this is a couple of solutions. One solution is pi half, the second solution is 3 pi half, and from here you get 2 more solutions. So this means the sine of theta is equal to minus 1/2. This happens at 7 pi over 6 and 11 pi over 6. Of course, we just have to look at theta from 0 to 2 pi, because theta from 0 to 2 pi gives us the whole curve. So this is for horizontal tangents, and for vertical tangents, we have to look at the denominator. Also here we get a couple of solutions. So from here we get 3 pi half, and from here we get the 2 cases where the sine of theta is equal to 1/2, which happens at pi over 6 and 5 pi over 6. Okay, so you see that if we look at horizontal tangents, then you see that because there is one case where both a numerator and denominator both equal to 0, so you have to consider this case extra. So for horizontal tangents, we have those 3 here. So pi half, not this one, 7 pi over 6 and 11 pi over 6. And for vertical tangents, you have 2 cases, pi over 6 and 5 pi over 6. And this, the final case, this one you have to consider extra. Because in this situation, both numerator and denominator are equal to 0. So what you are going to do here in this situation is to look at the limit as theta tends to 3 pi over half from the right and the left. So you have to consider those 2 limits. In both cases, you have to use the L'Hopital. And one of those limits will be equal to, if you approach from the left, will be equal to minus infinity. If you approach from the right, will be equal to plus infinity. It's something which you see already from the graph. So here for this final, for this critical case here, you have to look at the L'Hopital, the same expression, right and left-hand limit. But since we know in this case how the, or for this curve, how the graph looks like, or how the curve looks like, you see that because of this cusp here, so what we are discussing here is 3 pi half. Here you are essentially in this situation, and you could guess already from the curve that as you move to 3 pi half from the left, so you are here, the slope is negative, and the tangent will tend to minus infinity. And as you move to 3 pi half from the right, so this means you are approaching like this here, then the tangent is always positive, and it will, in the limit, it will be equal to plus infinity. So you can say in this sense, in this point, you have a tangent as well, a vertical tangent as well. Okay, and you see that, okay, so this means you have three horizontal tangents, 3 vertical tangents, and indeed you see them here. So here you have a horizontal, here horizontal, here horizontal, and vertical here, here, and here. Okay. So any questions to this? Now this is tangents. So how about areas? Areas of polar curves. Okay, so again we have given a polar curve. R is equal to f of theta. Assume that the function is larger or equal than 0. Assume that theta is between some a and b, where let's say b minus a smaller equal than 2 pi and larger than 0. So assume this situation. So this means that, okay, so our curve is, let's say this here. Let's say this is the polar axis. This is the pole here. This is the angle A. And let's say this is the angle B. And our function looks like this here. Okay, so what we want to compute is the area here of this region, of the region enclosed by the polar curve between A and B. Now, if you look at the more simple situation, namely a sector of the circle. So if this here is the radius and this here is theta, then we know that the area of the sector of the circle is equal to 1/2 times r squared times theta. So this would be for a circle. So by looking at this formula, it is quite easy to guess that in this general situation, so for this area here, you will have a similar formula. The only thing you have to do is you have to replace theta by d theta. You have to make the angle small, very small, and you have to add up over all such small sectors of the circle. Because you can approximate this roughly, maybe I should use another color. So you can look at a very small angle. D theta. And if this angle here is very small, what you see here is a sector of the circle. So what you have to do is, for this red part here, you have a contribution which is just given by this formula here. So 1/2 r squared times d theta. And what you have to do is to add over theta from A to B. Okay. So this is the formula we are going to expect. And of course, this is you get the same result if you look at limits. So what we do is, in order to prove this formula, is our usual approach. So we divide the interval from A to B into n subintervals. On every subinterval, we approximate the area by the area of a sector of the circle by choosing a sample points for every subinterval, where we evaluate f of so our function and take this as the radius of the sector of the circle which we are going to approximate. And we sum up over all those approximations and let n tend to infinity. And what you get is a Riemann sum, which will be equal to this integral here. Okay, so the proof you can find in our textbook, but it's the usual approach which we have seen already several times during this lecture. And I guess this formula is easy. It's also easy to memorize because it's intuitive. Now, maybe let's look at an example. A very easy example would be this one. R is equal to theta, where theta is between 0 and 2 pi. So what we have here is if we plot the polar curve, so here we have x and here we have y. So as theta is increasing, so theta starts at theta is equal to 0 and it increases to 2 pi. And as theta is increasing, r is increasing at the same time also from 0 to 2 pi. So this curve looks like this here. Okay, and what we want to find is, okay, what is the area enclosed by this curve here? Now you just plug into this formula, so you see the area is equal to the integral from 0 to 2 pi. Then you have a 1/2, which you actually can take out. And the function is very easy, so theta squared d theta is equal to, so this is the antiderivative. So what you get is 4 pi to the cube over 3 for the area which you see here enclosed by this curve here. It's slightly more interesting if you have two polar curves and you have to, so instead of one, you have now given two polar curves. And you have to compute the area which is enclosed by those two polar curves. Let's say call them f of theta and g of theta, and you have this relation here where theta is between a and b, and we have again that b minus a is larger or equal than 0, but equal than 0 doesn't make sense. Smaller equal than 2 pi. Now, again, this is the polar axis. So we have here the half line given by theta is equal to a, or the line given by theta is equal to a, and here theta is equal to b. And we have now two functions. So this is the function g, and this is the function f. And what we want to compute is the area which is enclosed by those two here, so this one. But of course, we can use the same formula. We just have to subtract. So this area is given by the integral from a to b. One half f square of theta d theta minus the integral from a to b, 1/2 g square of theta d theta. Okay, so let's look at a very easy example. For instance, if you have given those two polar curves here, r is equal to 4 times the sine of theta, and r is equal to 2. Okay, so the task is to compute the area which is inside this curve here, but outside this one. Okay, I should say inside the region enclosed by this curve here, but outside the region enclosed by this curve here. Now, if you have polar curves, the first thing you certainly want to do is to try to understand, okay, how does this region look like here? Now, in this situation, it's not so complicated because we discussed this polar curve last time. So this is just a circle. Okay, the radius of the circle is equal to 2, and the circle is located. The center of the circle is located on the y-axis. Okay, so you have this circle here. Okay, so this is the polar curve. R is equal to 4 times sine of theta. And also, this polar curve is a circle, but now the center is the origin of the coordinate system. So what you have here is this one. Okay, so this is R is equal to 2. And what you want to compute is the area of this region here. Okay, so the area of the region which is inside the region enclosed by this curve and outside the region enclosed by this curve here. Now, if you want to do this, okay, you just use this formula. But first, you have to find those 2 points of intersection here. Okay, for this, you just equate those 2 curves. So you see that in order to find the 2 points of intersection, you equate the 2 curves, and you get okay, sine of theta is equal to 1/2, and this is so theta is between 0 and 2 pi, because we look at the region enclosed by those 2 curves. So you see that theta is equal to pi over 6 and 5 pi over 6. Okay, so this angle here, this angle is pi over 6, and this angle 5 pi over 6. But we see that this region is symmetric. Okay, so we actually, in order to compute the area, or twice the area, let's write the area. The area is twice, and we just look at this piece here. Okay, and this piece is, okay, so we have the integral from pi over 6 to pi half. Okay, and then the upper curve. So we have a 1/2 here from this formula, so we can actually erase this. And then we have the upper curve, this one, so 16 sine square of theta. And then we have minus the lower curve, which is this one, okay, which is 4 d theta. Okay, and this is easy to integrate. So for this, you take the integral into 2 parts, and for the first one, you use the half-angle formulas. So this is easy to integrate here. So you see how to do this. So if you have given such an example, what you certainly want to do is you want to plot a picture. Okay, then you understand, okay, how the region looks like. Then you find the points of intersection, and then you just set up the problem. The rest is automatic integrating. Here I should maybe mention that it's sometimes not so easy to find here the point of intersections for such polar curves. You find a good example in our textbook. So you have to be careful in this step here. Just by equating those two equations, it's not always possible to find all points of intersection. The example which you find in our textbook is similar. You have a circle, and you have the cardioid. Okay, so this is 1, 2, 3. You see that the diameter of this circle is equal to 3. So the center is at 1.5. So you have this circle. And for the cardioid, okay, we have another color. Okay, and for instance, in our textbook, okay, the task is to compute the area of this region here. Now, the first step would be, as in this example, to find the point of intersection. So you see that what you do is, so those 2 points here, what you have to do is you have to equate those 2 curves. But this will give you the same equation as here. And you see 2 solutions. Which correspond here to those to the 2 points of intersection, this one and this one. Okay, but you see you have a third one, this one. It doesn't come out here from these equations. Who can tell me why? Why is it not possible to find this point of intersection by just equating those 2 curves? Who can see the reason? you see that, so those are the two curves, okay? I equate them to find the point of intersections. I get here in the intervals, what I'm looking at is the intervals 0 to pi. Okay, so the sign in this interval has two values where the function value is equal to 1/2. So you just get those two solutions here. Why not this one? The reason is very easy, because polar representation is not unique. So in particular for this point, for the pole, for 0, you have many different polar representations. Now, the reason why 0 lies at this curve here is because the polar representation 0 and 3 pi half satisfies this equation. Okay, the reason why 0 lies at this here is because here you have actually, because the polar representation 0 and k times pi satisfies this equation. Okay, but there is no common representation of the 0 of the pole which satisfies both equations. Yet the 0 is on both curves, but using different polar representations. Okay, so because the polar representation is not unique, that's why if you have two polar curves, you want to find all points of intersection. It's not that simple. It's not. If you equate those two, you might lose some. So if you have to find all points of intersection of two polar curves, you should draw a picture. This is important. Otherwise, you will lose out solutions. Another good example is this one, which is also in our textbook. This polar curve we also discussed last time. Okay, so this polar curve looks like this here. A rose with 4 loops, or 4 leaves, like this one. Now, if you intersect this polar curve with this one, r is equal to 1/2. So you see, if you do this, because this length here is 1. So if you do this, you have here, how many points of intersection do you have? 8. Okay, but if you just equate them, so the cosine of 2 theta is equal to 1/2. Okay, because this equation, okay, you look at two periods of the cosine, because the theta is as always between 0 and 2 pi. Otherwise, things are just getting periodic. Okay, so what you do is, okay, you look at this here. So you look at the situation when the cosine of 2 theta is equal to 1/2, and you see only 4 solutions. Okay, so you just get 4 of those points here. For the other 4s, you do not get like this. Okay, so the best thing is either to draw a picture, and from the picture, from symmetry, you can deduce the other 4. Or here in this situation, it would be possible to compute the other 4s. You have to use another representation of the circle here, namely, you have to replace this by this one. Then you would get the other 4. Okay, so the main message is, if you have two polar curves and you have to find all the points of intersection, you have to be careful. Okay, always plot the picture, otherwise you might lose some of the points of intersection. So be careful if you do this. Okay, so any questions to this? So these are areas. Now, the last question I want to discuss concerning polar curves is how to compute arc lengths. Also, this is, of course, easy, because we know already how to compute arc lengths for parametric curves, and polar curves are just special cases of parametric curves. Okay, so arc lengths. Okay, so again, we have given a polar curve, theta from A to B. So this gives us some curve in the Cartesian coordinate system, and we want to find the length of the curve, the arc length. So again, we will use that x is equal to f of theta times the cosine of theta, and y is equal to theta times the sine of theta. Okay, so the polar curve is given by these parametric equations, and for a set of parametric equations, we know how to find the arc lengths. So the length is equal to the integral from a to b, then the square root of dx over d theta square plus dy over d theta square d theta. This is the usual arc length formula for curves given by parametric equations. So what we have to compute is dx over d theta. Okay, so here we have to take the derivative with respect to theta. So what we get is the derivative of f with respect to theta times the cosine of theta plus f of theta, the derivative of the cosine, which is minus the sine, and dy over d theta, similar, the derivative of f with respect to theta, the sine of theta, plus f of theta times the cosine of theta. Now we have to square this one and add the square of this one. So you see, from this you see that dx over d theta square plus dy over d theta square. So you have to compute the square of this one. But you see, because of the minus, and because you have everywhere sine, cosine, f theta, the derivative of f theta, the mixed terms canceling out because one is minus, one is plus. So you just have to look at the square part. Now you have this square plus this squared, but you can take out the square of the derivative, and the rest is equal to 1. So what you have, this one for this one, and here this squared plus this squared, but this is just, because of the same reason, it's just this one. So what you get is, this is the integral from a to b, the square root of, now let's maybe write this as dr over d theta square plus r square d theta. So this will be the arc length formulas for, this will be the arc length formula for polar curves. Okay, and if you want to compute, so if you want to compute the length of a polar curve, it's now very easy. You just plug in into this formula here. Okay, so for instance, if we look once more at the cardioid, okay, so what is the arc length? What is the length of the cardioid? Theta from 0 to 2 pi. So the L is equal to the integral from 0 to 2 pi. So the derivative here with respect to theta is the cosine of theta. So you have here cosine square of theta plus, and plugging this in here, you have 1 plus sine of theta square d theta. Okay, so this can be now simplified. So you have the integral from 0 to 2 pi. Now here you have, so if you square this out here, you get 2 plus 2 times the sine of theta d theta. And maybe it's worth it to discuss this integral here, because this integral is a little bit more tricky than the integrals we have encountered so far. This example you find in our textbook. So you can write this as square root of 2 integral from 0 to 2 pi, and then the square root of 1 plus sine of theta d theta. Okay, so the question is how to compute this integral here. Now, our textbook suggests you multiply both. You multiply with square root of 1 minus sine of theta, and then square root of 1, and divide by the same term, because then you get in the denominator the square root of 1 minus sine square, which is the cosine square. So you get the root of cosine square of theta over. And here you have to be careful because of the range here of theta. You are not allowed to drop here the absolute value. Okay, so the absolute value has to be considered. Okay, so this is one possibility to solve this integral. Maybe a little bit tricky because you have to think that you have to come up with this trick here. But of course, there are many other ways to compute this. Maybe another way, which I would prefer if I see such an integral, is using half-angle formulas, because you know that the cosine of theta half is equal to, so here actually a square, 1 plus the cosine of theta half. But here you have 1 plus the sine of theta. But if you take the square root here, you almost have the integrand. Okay, but it's easy to switch from the sine to the cosine, because this is equal to the square root of 2, the integral from 0 to 2 pi, and then you just replace the sine of theta is equal to the cosine of pi half minus theta. Okay, now you substitute u is equal to pi half minus theta, so you have here square root of 2. Now, from the d theta, the minus d theta is du, so you get a minus, so we already interchange upper and lower limit, so you have here pi half, and here you have minus 3 pi half. And then you have here the square root of 1 plus the cosine of theta, d theta. Okay, now, or du maybe better. Now you can, now you can really use this formula here. Okay, so you can replace this here by square root of 2 times the cosine of theta half, but again you have to be careful because of the sine. Okay, because you see that if you look at the lower limit, okay, at the lower limit, this argument here is minus 3 pi over 4, and here the cosine is negative. Okay, the cosine will stay negative until minus pi half, and for the remaining range, which corresponds here to pi, for the remaining range, the cosine is positive. So you have to be careful here. So this is the square root of 2. So you have to break this here, this integral, into 2 parts before you use this. So from minus 3 pi half to minus pi, square root of 1 plus cosine of u du, plus the remaining part from minus pi to pi half, square root of 1 plus cosine of theta du. Okay, so if you take the square root here on both sides, okay, you see you can replace this here by 2 times the square root of the cosine square. Okay, but in this range, okay, maybe I should plug this in slowly. Okay, so you have here square root of 2 times the square root of cosine square of u half du plus the integral from minus pi to pi half, and then again the square root of 2 times the cosine square root of u half du. This looks maybe a little bit stupid because I have here a square root of a square, but I have to write it like this. I want to write it like this just to make it clear that here what you get is minus cosine of u half, and here what you get is cosine of u half. Okay, because of the range here. So you have you take out the square root of 2, so you have 2 here, and then you have the integral from minus, and here you have minus cosine of u half du plus, and here you have plus. Okay. But now the integral is easy to solve. Now you have, so the integral is, an antiderivative of this function is this one. Yeah. Evaluated at minus 3 pi half and minus pi plus. And here the same antiderivative. Okay, so you see that here at the upper limit, this is -1, so everything becomes +1. So what we have here is 2 minus the square root of 2 plus, and then we have square root of 2 plus 2. So the answer is 8. And this answer is the same, should be the same as in the textbook. Okay, so you see that this integral, not so easy as it looks like. Okay, I mean, it's not very complicated, but you have to be careful, okay? Because we are used to it that whenever we see the square root of a cosine square, then we just replace it by a cosine. But you have, if you have a definite integral, you have to look at what is the domain, okay? And whether if you have a square root of like here cosine square, whether in the given domain the cosine is positive or negative, you have to take the sign into account. Okay, so any questions to this? Now this actually concludes the course in this semester. Next semester we will go on and learn more or less. We will next semester the course will more or less be divided into three big topics. The first one is looking at series and sequences. Second one is we are going to extend everything we have seen so far is for functions of one variable. So most of the time we consider the function y is equal to f of x, only one variable. Now what we mainly looking at next semester are functions of more than one variable. So for instance, you have z is equal to f of xy, and we wanna ask the same questions which we have asked and answered during this semester, namely how to compute or is there a good notation of derivatives? How about integrals? And so on. Roughly speaking, next semester the course will be divided into 3 parts. The first part is sequences and series. The second part is the theory of differentiation for function of more than one variable, and the third part is the theory of integration for functions of more one variable. Okay, so any questions? Okay, so if not, then here's your final.